Hi, this is Roger from Kainka Labs, and today we'll talk again about demagnetizing. In a previous video on our long time video series about what every maker should have, I did show you the use of such a magnetizer and demagnetizer for ion tools like screwdrivers. And as you already could see in the demonstration, the demagnetizing was not very, well, let's say reliable or not very repeatable. So demagnetizing apparently is a bit more complicated. And at the end of the video, I'll explain to you how perfect demagnetizing can be done for tape heads, which were used for you young timers in tape decks or cassette decks in earlier times, because the tape head becomes magnetized after some time, and this gives you noise on your tape. And there are tools like this TDK tool for demagnetizing, and I did show you how the signal waveform generated here in the front, where there's a coil inside. Just take a look at the video and you'll see it. And I told you that there are basically two methods for perfectly demagnetizing magnetic materials. That is either heating them up above their so-called Curie-Temperature. Their magnetic materials lose their magnetic properties, and when they cool down again, they are perfectly demagnetized. But that, of course, is not a good idea, neither for tools nor for tape heads. But I also told you that it's very important that such demagnetizing tools have a decreasing sinusoidal field. And now let's take a look a bit more into the theory, because the theory of magnetic materials, you will meet them at many instances, like transformers or magnetic electromagnets and so on, magnetic transformers, radio frequency transformers, or ferrite antennas and so on. Now, for that purpose, there is a very important diagram, and the most difficult thing to understand in the end is what the different axes, the x and the y axis, what the meaning of this letter H, which is the so-called, in technical terms, the coercivity, and the letter B, which is the so-called induction. Now, if we give these two designations a more understandable word, namely, this is the field strength of an external field. You can suppose you take an electromagnet, and the coil and the current through your coil of your electromagnet, of course, as you will know, generates a magnetic field. And the field that is externally generated, usually by a current flowing through a coil, that's H, the coercivity or the field strength of the externally generated field. Now, when you put a magnetic material like iron in the middle of the coil, and that's exactly how an electromagnet works, then this external field induces a field in the magnetic material. You also can see this as the magnetic material, usually iron or ferrite, amplifies the external field. Now, this is let's call this the induced field in or by the magnetic material. So that is the basic to understand how the curves that we now draw, what they mean. So let's suppose we take a totally unmagnetized material, a piece of iron, and we start with, of course, with 0 field strength of the external field, just when we have no current flowing through the external coil, and then we ramp up the current, and then we get a increasing, as we ramp up the current, we get a linearly increasing field strength. And now what will be the induced field by the magnetic material do? It will also increase, but not in the way that you perhaps suppose. It will not go linearly up, but for example in a shape like this. And now, so it's not a linear relation. That's the first thing you have to know. And now, just to make it not all too confusing, we will just draw again basically the same graph, but now without too many explanations. So now you might think, once we have now induced a certain induced field in here by the external field, what happens when we switch, when we either ramp down the external field, or if we simply switch the electromagnet off? You might think, well, then usually, as from experience, the induced field would go backwards on the same curve, but it does not. It goes around this way. And there will remain some magnetism even if the external field has gone back to 0 again. So that's the first thing that makes magnetic materials a bit more complicated, like, for example, capacitive materials, where there's usually a very linear relation between external, in that case, voltage and the induced voltage. So here we get, even though there is no more external field present, we get a remaining field, or this point is called the reminiscence, and that also explains what it is. And you might know from experience that this is also a way to get from an unmagnetized piece of iron to a permanent magnet made out of iron. That's how you do it. You create an external field with a coil, as in an electromagnet, then you switch off the current, and the induced field does not go back to 0, but there remains a certain remnant magnetism, or the absolute value is called the remanence. So that is now the state that we have if we have a permanently magnetized piece of iron or any other piece of magnetizable material. And now the task is, how do we get rid of the remanence and get back again to 0 remanence? As we have seen, this does not work by simply switching off the external field. We have to do something else. Now, your first idea might be, well, very easy. We reverse the current and make the external field a negative value, and then we should get back to 0 again. Well, let's see what we actually get. When we now make we ramp up again the current in the external coil, but this time with reversed direction. And what does our curve here make? The induced field in the magnetic material, well, of course it will go through 0, but we don't know when this point happens, and so usually you go either you are here on this point or here, so you're not sure to reach exactly this point. And even if you would get this point, again, if you switch it off, it would go back to another remnant point. So we now go back to what's called the saturation. As we already could see here, there is a point when you can increase the external field however you want. There is a maximum inductance that any magnetic material can reach, and that is called saturation. That is simply the point when all the so-called magnetic domains, which you can imagine as the very small mini magnets, when they are all fully magnetized, then however your external field, however great it becomes, whatever value it takes, you can't magnetize more than all mini magnets, all magnetic domains in a magnetic material. So we have drawn exactly to this saturation point, and you also can see this here. Here it starts to saturate, and here we again have the point of maximum induction, in this case in the other way, so this is minus B. So that means that north and south pole of your magnet are simply reversed. We are again here in the saturation. And what happens when we now, for example at this point, switch off the external field? Well, again, the induction, the generated magnetic field by the magnet does not go back to 0, but it goes back around to this point, the negative. It is the same value as here above, but with polarity reversed. North and south pole are reversed. So we can repeat this many times. We always get some kind of remnants, and this is not the way to go from saturation to demagnetize a magnet. So there must be a trick how you can, with this complicated curve, how you can deal with it to really demagnetize a magnetic material. And that's the next thing we draw on our next piece of paper, or show on the next graph. So, and this is the magic graph that gives us a hint how we can demagnetize. Again, this is the 0 point where we want to get to, 0 inductance B. Here again at the x-axis we have the external field H, and on the y-axis we have the induction, which is measured in Tesla. Now you know where the word Tesla is used in physics. Now let's suppose we start by completely driving our magnetic material into saturation. With the first period of our signal we go into positive saturation, and to be sure, the next part we reverse the current of our external field and go into negative saturation. The reason is we don't know beforehand if our magnetic material is positively magnetized or if it has a negative remanence. So to be sure, we first magnetize it fully on the positive side and then fully on the negative side. That's why I said in the other video that the first two half waves of a sine wave, let's suppose we change the external field simply with a sine wave. We go first up, then the sine wave goes to the negative maximum. So now we can be sure we are at this point of the induction curve. And now the next part of the sine wave, so let's suppose we now don't take the external field to the full field strength, but we go a little bit lower, only to this point. Now, if we now switch off the external field, we get a lower remanence, excuse me. We get a lower one that we got initially from saturated magnetization. So we are at least one step nearer to our 0 point if we go either from the positive or from the negative side now to a slightly lower maximum magnetic external field. And if the next part of the curve, when we swing again back to negative values, we are now again at a slightly lower maximum external field, then we get a remanence this time on the negative side, which is in absolute values again slightly lower than at the second cycle. And the next cycle will be the light blue one. We go again to the positive side, but again with the maximum field slightly lower than before, and we get a remanent magnetic field in the ion, again slightly lower than before at the green curve. And we repeat this and let the amplitude of the external field, which in our example is simply sinusoidal, we simply diminish the amplitude step by step, and we'll get nearer and nearer to the 0 point. And if in the end we will reach exactly with a totally demagnetized material. So let me once again repeat. We take a sinusoidal wave with a decreasing amplitude, but which starts with a the first half wave goes to a maximum where we know that the material is fully magnetized, which means that we go into saturation, and this, to be sure, the next half wave will go into negative saturation, and then the maximum amplitude, the peak amplitude of every half wave decreases and decreases and decreases, and the effect will be that the remanent magnetism of the magnetic material will decrease with every half wave. It changes from positive to negative, but that doesn't matter. What matters to us is the absolute value of the remanence, and it finally reaches exactly 0. Now, how do we reach this purpose in practice? There are two simple ways. Let me take a clean piece of paper. what we need is, we now know a sinusoidal wave which starts with two relatively high peak amplitudes, which saturate the material first on the positive, then on the negative side, and then the amplitude goes, it mustn't be exponentially decreasing, but it needs at least to be steadily decreasing until it tapers down to 0. And we can do this either electronically. Perhaps I will, in a further part of this video, will take apart this electronic demagnetizer, and I'm quite sure that it works simply by charging up a big capacitor. That's why it takes a few seconds until the green light lights up that it's ready. And then there will be a tank circuit, a circuitry where a capacitor and the coil, the inductance here in the front of the demagnetizer, where they build a resonant circuit. And because the charge of the capacitor, because we have resistance and other losses in the tank circuit, as you know from any oscillator circuit, the amplitude will slowly decrease depending on the parasitic resistance and other factors, and that's how you can reach this form, this shape of the decreasing sine wave electronically. The more simpler way is you take a big choke which you can directly connect to your 50 Hz or 60 Hz mains voltages, and when you draw this choke slowly away from your tapehead which you want to demagnetize, then of course also the field strength will decrease around with the square of the distance, or with the inverse of the square of the distance, and that way you can manually or mechanically also generate such a slowly decreasing field strength or sine signal by simply pulling away a choke from your tapehead. But you have to do this very cautiously. You should do it with a very even motion and not make a fast any fast movements. So that's why the electronic way to doing this is much more comfortable and much more reliable. So I hope this could explain a little bit what's sometimes quite complicated, the theory of the magnetic curve, and that there is not only one such curve, but that depending on the field strength, the curve, the magnetic curve of any magnetic material takes on this shape, which looks a bit like a hysteresis curve, and that's also why it's called magnetic hysteresis curve. You saw where the induction, where the word Tesla or the unit Tesla is used, and now you know how to demagnetize tapeheads with either an electronic device or a mains connected choke. And well, I hope you liked it and you could learn a little bit, and well, see you next time, and perhaps with a take apart of this TDK HD11 electronic tapehead demagnetizer. So that was it. Bye from Kanka Labs, bye from Roger. Until next time.